From the world's longest tunnel to the new Chernobyl safety arch and the biggest ship ever built, in this video, we take a look at some of the world's most impressive megaprojects. April 26, 1986 is a date that will live long in the memory. At 1:26 a.m., the core of reactor number 4 at the Chernobyl nuclear power plant in Ukraine exploded in the dead of night. An immense explosion blew the 2,000-ton concrete reactor cover nearly 15 meters into the air. It was the starting point for what would become the world's worst nuclear accident. It was marked by the Chernobyl cloud, a radioactive plume that crossed much of Europe. The disaster also concealed an unprecedented construction adventure: the building of the Chernobyl sarcophagus and today's immense containment structure. A radioactive epic begun just 1 month after the disaster by Soviet engineers and partly completed in 2019. In this new episode of Looking For, I take you to the heart of this unprecedented construction site to present all the challenges of the Chernobyl Arch, a megastructure unique in the world. With its 108-meter height and 257-meter span, the Chernobyl Arch is enough to enclose the Statue of Liberty, a gigantic arch whose steel structure alone weighs 25,000 tons. With such dimensions, this type of structure would inevitably have been complex to build anywhere, except that the structure, which began construction in April 2012, is located on a site surrounded by forests and swamps, a long way from the factories where the building materials are manufactured, and with winter temperatures that can drop to minus 30 degrees. But these difficulties pale in comparison with the radioactivity of the site, which will radically complicate the construction work. Surrounded by 200 technicians from 21 different countries, 1,200 Ukrainian workers have been working in the 30-kilometer exclusion zone established following the explosion. Their mission? To construct a building capable of containing the damaged reactor in a durable and, above all, leak-proof manner. In 1986, the Chernobyl region, like the rest of Ukraine, was a Soviet Socialist republic, one of the republics of the Soviet Union, the USSR. In the months following the explosion, Soviet engineers erected an initial steel and concrete sarcophagus to serve this purpose. Just 2 months after the disaster, 90,000 workers went to work from June to November 1986 to build the Chernobyl sarcophagus. But the urgent need to act and the dangerous nature of the work resulted in an unstable, leaky structure, which over time and in adverse weather conditions deteriorated significantly, to the point of presenting a serious risk of collapse, which could lead to further dispersion of radioactive material. Concern is heightened by the fact that 90% of the 200 tons of fuel present inside the reactor at the time of the explosion are still there. In the late 1990s, consolidation work was undertaken to deal with the most urgent problems. This work was intended to provide some 15 years of respite. After gaining independence, Ukraine decided to take a long-term approach to the problem, and in 2004 launched a call for tenders to design, build, and commission a new secure containment facility. Several construction giants responded, but in the end, Novarka, a consortium specially set up by the French companies Bouygues and Vinci, won the bid with its metal arch project. The aim of this containment structure is not to stop radiation, which rapidly becomes negligible with distance, but to prevent further contamination of the environment through leakage of contaminated particles. To fulfill this barrier role, a steel structure with stainless steel inner cladding was designed. External cladding on the frame protects the damaged reactor from external aggression. However, the signing of the contract in September 2007 marked the beginning of a long series of difficulties, since working in a radioactive zone implies taking health precautions, which are just as much a technical challenge. Although radioactivities now fall into almost normal levels in most of the exclusion zone, the problem remains that large quantities of radioactive debris were buried all over the site in the months following the accident, and no precise mapping of these dumps exist. So, even before starting construction of the containment building, Novarka first had to completely clean up the area on which it planned to establish its future work site. An area of 90,000 square meters where thousands of tons of soil, vegetation, and radioactive waste had to be excavated and replaced by sand to an average height of 1 meter. And to further limit the radiation emanating from radioactive sources likely to lie below the level of the stripping, the area was covered with concrete slabs. Another exceptional measure taken to limit workers' exposure was to set up the site not around the reactor to be covered, but 300 meters from it. This remoteness means that the workers can work without the protective equipment specific to radioactive environments. They're simply fitted with a mask in case of an incident and 2 dosimeters to check their level of exposure. Only once the vessel's been built will it be transported to the reactor. This is an unprecedented challenge for Novarka's engineers, since they have to move 36,000 tons horizontally over a distance of 300 meters. A world first that will make the Chernobyl arch the largest mobile structure on Earth. To achieve this, the giant arch rests on rails of sorts known as long rines, huge reinforced concrete beams with Teflon-coated surfaces. This material, combined with the stainless steel plates beneath the arch's feet, reduces the intense friction forces that will be exerted when the arch is pushed into its final position by hydraulic jacks. In keeping with the same concern to work as far away from the reactor as possible, the Chernobyl containment system was built in 2 stages. First, a first half arch was built, then placed in an intermediate zone, halfway between its construction site and the reactor, to leave the construction area available for the second half arch. As with the first, Novarka's engineers opted for a surprising procedure. It wasn't the walls that were built first, but the roof. Indeed, an arch of this size can only be stable once closed, which is why the upper part was built first. Once completed, it was lifted 30 meters using lifting towers designed to hoist loads of tens of thousands of tons. The lower elements were then added to the space left below, and the whole structure was then raised again by 30 meters. In the end, 3 lifting operations per half arch were required. In 2016, a system of pulleys and hoists was installed to enable what remained of the damaged reactor to be dismantled. 2 overhead cranes, each with a lifting capacity of 750 tons and a length of 100 meters, are also lined up inside the structure to carry the tools and robots required for future dismantling. Once the arch had been fitted out, it was pushed over the reactor 330 meters away. This operation, which took place in November 2016, lasted almost 13 days. But the new containment system won't be fully operational until July 2019. This long waiting period can be explained by the fact that the containment was not designed solely to confine the reactor. Its purpose is also to enable the current sarcophagus and the reactor's remains to be dismantled under optimum safety conditions. Because of the radioactivity involved, these operations can only be carried out by machines and robots. In fact, the containment vessel is so large not only because of the size of the sarcophagus to be covered, but also, and above all, to accommodate these machines. To enable these operations, Novarka's constructed technical buildings. They act as access locks to the arch for personnel, equipment, and the removal of products from the damaged reactor. Secondly, they house the equipment required to operate the facility, such as ventilation and power supplies. Finally, they provide a hall for the preparation and conditioning of dismantling products prior to their evacuation to the outside world. These 3 functions meant that the buildings had to be located very close to the arc, where the radiation was more intense. As radiation stopped by concrete, temporary concrete walls were first built to protect the workers responsible for constructing the buildings. And to limit their exposure time, they were taught and rehearsed in a school several kilometers from the construction site. But behind this extraordinary construction site remains an unanswered question. When will dismantling take place? The only certainty is that the containment arc is guaranteed to last for 100 years. According to the experts, this is enough time to develop the technologies needed for the dismantling operation, finding the solution, but also finding the money. Even before decommissioning, the containment systems already cost almost 1.4 billion euros, almost twice as much as originally planned. Only time will tell whether this super arch will indeed be Chernobyl's final resting place. Now we're off to Switzerland to see how the world's longest tunnel was built. But first, let me introduce you to your new best friend against web threats, Surfshark, the sponsor of our video. Surfshark is a VPN that lets you change your location on the internet with a single click, effectively protecting you against online threats, identity theft, or even content censorship in certain countries. If, like me, you work a lot on the move and you're not at ease when you connect to the public Wi-Fi at a railway station or even in your hotel room, Surfshark VPN will give you real peace of mind, as it effectively secures your internet connections while protecting your sensitive data from potential hackers by encrypting it. This is ideal when you need to send sensitive files to your company or customers. But that's not all. Surfshark also contains other useful complementary security services such as Surfshark Antivirus or Surfshark Search, which lets you search online without being polluted by advertising while preventing websites from tracking your data by making your browsing confidential, so you're effectively protected against online threats. If you subscribe now, you'll be able to take advantage of an exclusive offer and 4 additional months free of charge via my link in the description just below. What's more, you'll get your money back for 30 days, so it's safe to try. It's a colossal project, costing over 12 billion euros, that has reshaped the map of Europe, the longest railway tunnel ever built. Cutting through the St. Gothard Massif in the Swiss Alps, this endless tunnel brings Switzerland and Italy closer together via a high-speed rail line and reduces truck traffic crossing the country by transferring part of road freight transport to rail. But the construction of this gigantic tunnel was a very long and hard process. In this new episode of Looking For, I take you deep into the Swiss Alps to discover the technical challenges that had to be overcome to achieve this engineering feat. Located between the towns of Erstfeld and Bodio, the Gothard Basis Tunnel is a megaproject whose construction began in the 1990s. Since it opened to commercial traffic on December 11, 2016, it's cut through an immense wall of rock rising to over 3,600 meters, over a length of more than 57 kilometers. Still unrivaled to this day, it remains the longest railway tunnel in the world, surpassing the famous Channel Tunnel by more than 6 kilometers. Launched in 1994, construction of the tunnel mobilized some 2,400 people who worked around the clock to keep the site moving. Workers, engineers, surveyors, and many other trades essential to such a challenge worked together to build this exceptional tunnel. Whereas the previous railway tunnel was located at the summit of the Massif, the new structure is located at its base, offering the advantage of being almost in a straight line with very little gradient. Stretching from 300 to 560 meters in altitude, it has a maximum gradient of 12 meters per kilometer, more than half that of the historic line, which stood at 26 meters per kilometer. This is a game-changing advantage, as freight trains no longer have to climb the mountain's twists and turns, and no longer need an extra locomotive to push the convoy. As a result, the new Gothard Basis Tunnel can reduce energy consumption by a half, even with longer, heavier trains, and save 45 minutes on the journey between Zurich and Lugano. Today, 260 freight trains can travel through the tunnel at a speed of 160 kilometers an hour, compared to the 180 trains that used to run through the historic tunnel. Speaking of history, the old railway tunnel, inaugurated in 1882, was a real technical feat for its time. Running almost 15 kilometers, 1,000 meters below the summit of the Gothard Massif, it became the longest tunnel in the world at the time. It was dug from both ends using the brand new dynamite patented by the famous Alfred Nobel in 1867. Today, this historic tunnel continues to be used as a fallback solution in the event of the high-speed line being closed due to an incident or repairs. But it's not just freight that benefits from the new tunnel, passengers too. Since 2020, with the completion of the 15.4-kilometer Cineri Extension Tunnel, the high-speed line between Milan and Zurich has saved almost 1 hour, from 4 hours 10 minutes previously to just 3 hours 17 minutes today. The maximum speed allowed in the tunnel is 200 kilometers an hour, which is 40 kilometers an hour more than the Eurostar speed limit in the Channel Tunnel. But let's leave the trains aside for the moment and turn our attention to the technical aspects of this gigantic tunnel. The Gothard Basis Tunnel consists of 2 parallel tubes, each over 8 meters in diameter and spaced at around 40 meters apart. Each tube accommodates a one-way track. However, there's no additional tube to evacuate passengers in the event of an accident, breakdown, or fire, as is the case in the Channel Tunnel. Instead, transverse galleries connect the two tubes every 325 meters. These allow stranded passengers to reach the adjacent tube. The tunnel's also equipped with two emergency stop stations in the event of a problem. The tunnel's designers installed smoke extraction chimneys and powerful ventilation systems at these stations in order to prevent any disaster. In the event of a fire in one of the tubes, the safety equipment creates excess pressure in the second tube, preventing smoke from entering and allowing passengers to escape into the fresh air. In addition, the stations also house two exchange rail diagonals, enabling trains to switch from one tube to the other if necessary, as in the case of maintenance work on the track. As well as being ultra-safe, this extraordinary tunnel also presents a number of technical challenges. The first challenge was to find the best route through the Gotthard mountain range. The alpine fold that gave rise to the tunnel is a veritable geological millefeuille. In fact, some 20 layers of rock follow one another vertically along the tunnel route. Some, made up of granite and gneiss, are very hard, which is perfect for the project. Others, on the other hand, are more friable, and this is where the problems begin, as special consolidation techniques are required. Before starting work on the project, geologists had to identify the rock types in the massif. The problem was that the tunnel to be built was not only the longest ever dug, but also the deepest ever built. In fact, in some places, the rock covers up to 2,300 meters thick. At such depths, it's impossible to be sure of the nature of the subsoil, so we had to extrapolate from faults identified by aerial photography. A series of boreholes and information accumulated over the past century. Two zones presenting the greatest geological risks were quickly identified. The first, in the middle of the route, is the Tvech Intermediate Massif, on which the village of Sedrun lies. It contains a high proportion of brittle rocks, known as kukurites. The second zone, near the commune of Fado, is a deep vertical geological fold, the Piora syncline, formed of saccharoid dolomite, a sedimentary rock. A real calamity, since this granular rock, like powdered sugar, is soaked up by water infiltrating the mountain. And the further down you go, the greater the pressure exerted by this water column. At a depth of 900 meters, the pressure is 90 bar, which is as high as if you were 900 meters underwater. These difficulties at Sedrun and Fado had two consequences. Firstly, they affected site organization. Rather than digging the two tubes from their ends at Erstfeld and Bodio, intermediate attack points were added at Amsteg, Sedrun, and Fado, with several access tunnels to lower men and material to the future tunnel site. At Sedrun, the first of the two ventilation shafts, 850 meters deep and 7 meters in diameter, was equipped to serve as an elevator and freight elevator during the construction work. All in all, over 150 kilometers of tunnels, galleries, and shafts were dug. In this way, the double tunnel was divided into 5 sections, ranging in length from 8 to 16 kilometers. All of these separate construction sites were run in parallel to reduce construction time. The nature of the rock expected along the route also determined the choice of excavation techniques. The solid granites and gneisses of the Erstfeld, Amsteg, and Bodio sections were attacked using 3 tunnel boring machines, capable of cutting through 10 to 30 meters of rock per day. 2 of them were lowered in pieces to Amsteg via a 1.8 kilometer access gallery. It took several months to assemble them. Monsters weighing 3,000 metric tons and over 400 meters long. They were custom built in Germany to adapt to the rocks they would have to eat along the way. With a diameter of almost 9 meters, their impressive drill head houses 58 cutting wheels. Each one shatters the rock with an enormous 26 tons of pressure. On average, these rock eaters will have advanced at a speed of 15 meters per day. However, there were some less pleasant surprises. The Fado emergency stop station, for example, had to be moved 750 meters to the south due to poor rock quality. As for the Sedrun section, the TBMs were in danger of getting stuck in soft rock. Only the conventional method, using explosives or hammer drills, was suited to the particular nature of these rocks. First, the rocks consolidated and then shattered. Large quantities of concrete are shot into the rock. Then safety anchors, metal bars several meters long, are inserted to nail the rock. Drilling machines then bore holes 4 meters deep, into which up to 400 kilos of explosives are placed. But this technique is much slower than TBM's and progresses at a rate of only a few meters per day. Despite representing only 15% of the tunnel, the Cedron section took as long as all the others combined, 12 years. In the end, 80% of the main tubes were excavated using tunnel boring machines and 20% using conventional explosives, for a total of 28.2 million tons of excavated rubble, the equivalent of 5 Khufu pyramids. Whatever the excavation method used, a second step's essential as soon as the wall's excavated. The vault must be consolidated straight away. Otherwise, the cavity, under the pressure of the rocks, risks shrinking or, worse still, collapsing. A whole range of techniques is available: anchoring, laying wire mesh, spraying concrete, using hangers, all of which can be combined. The aim is not to prevent deformation at any cost, but to limit it. In some places on the Cedron section, the freshly excavated rock exerted a thrust of 20 megapascals, or 2,000 metric tons per square meter. No system can withstand a load that great, so we have to allow the rock to deform to reduce the pressure, explains Heinz Urbar, former technical director of Alp Transit Gotthard. To this end, engineers developed an innovative system of sliding hangers specifically for the Cedron site. Interlocking, the hangers form a ring that can be retracted. This flexibility allows the ring to follow the deformation of the rock, so that the pressure decreases before blocking it. Once the first vault's been built, a cushion lining and then a 5 mm thick waterproof layer cover it to protect the second vault from water infiltration. The inner vault, built in concrete and protected from seepage, is designed to withstand rock thrusts alone for the tunnel's 100-year lifespan. Beyond that, reconsolidation work may be required to extend the operating life of the tunnel. In the end, the civil engineering work was completed on March 23, 2012, when the last concrete block was poured. This was a relief for the crews, who worked day and night in difficult conditions, as the average temperature in the tunnel was 28 degrees Celsius, thanks to a water cooling system. Without this system, the temperature would otherwise have averaged 45 degrees Celsius. The final stage in this titanic project is the installation of the railway installations that will enable the tunnel to be operated. Tracks, points, power supply, radio and telephone links, not forgetting of course the signs for train traffic. Unlike most other tunnels, the Gotthard tunnel has no light signals. Instead, positioning beacons on the tracks ensure that the location of trains in the tunnel is always known. A specific software system for preventive incident detection is also installed. Based on information sent by the trains, automatic scenarios can be triggered, such as the activation of the tunnel ventilation system in the event of prolonged stoppage of the train in the middle of the track. With this tunnel, inaugurated on June 1, 2016, Switzerland can congratulate itself on having achieved the record for the longest railway tunnel ever dug, for the third time. In the end, it took 22 years to complete the tunnel, and a further 4 years if we include the additional Cineri Basis tunnel, completed in 2020. But unfortunately for the Swiss, the Gotthard tunnel won't remain the longest for long, as another megaproject is soon to overtake it, the Mont Cenis Basis tunnel. Construction of this megaproject began in 2016, and it's set to extend 400 meters beyond the Gotthard tunnel. It'll enable France and Italy to bring the cities of Lyon and Turin closer together via a transalpine high-speed line. Scheduled to come into service by 2030, the line should save 2 hours on the current journey time, which stands at 4 hours 15 minutes for the fastest connections. This is the world's largest floating structure. Its name is Prelude Flng, and its dimensions are truly gigantic. 74 meters wide, 100 meters high, and 488 meters long. So massive, in fact, that it could withstand the most ferocious waves. By way of comparison, Prelude is 128 meters longer than the Harmony of the Seas, the current holder of the title of the world's largest cruise ship, which at 362 meters is already very impressive. It's even 30 meters longer than the Seawise Giant, the largest supertanker ever built. Quite simply, Prelude is so enormous that you'd almost have to leave the shipbuilding industry to find a match for its sheer size. In fact, if it could be placed vertically, it would rival the Taipei 101 Tower in Taiwan, one of the world's tallest skyscrapers. With its full tanks, the Prelude station could weigh in at over 600,000 tons, the equivalent of 430,000 medium-sized, and it took 260,000 tons of steel to build, the equivalent of 35 Eiffel Towers. A true monster of the seas, not designed to carry containers from one end of the planet to the other. In fact, it's a real floating facility designed to extract and liquefy natural gas in the sea. Conceived by the oil company Royal Dutch Shell, the project's been named Prelude, after the name of the first gas field to be exploited in the Browse Basin, 200 kilometers northwest of the Australian coast. So why set up a liquefaction plant in the middle of the ocean? Well, it's mainly for financial reasons. Once extracted from underground aquifers, natural gas is transported from the platforms to land via endless pipelines, which can often exceed 1,000 miles, to reach the plant where it is then liquefied. This change of state transforms the gas into a liquid, reducing its volume by a factor of 600. A way of optimizing gas storage before it's shipped to its destination market. These links between extraction platforms and liquefaction plants, added to the costs of subsea maintenance, require very heavy investment, hundreds of millions, even billions of dollars, investments that only become profitable for very large gas fields. However, global demand for natural gas is booming, and we now need to exploit smaller offshore deposits that are not profitable enough for this type of installation, and yet account for 40% of the world's gas reserves. It was then that the new concept of a floating facility began to emerge, with a triple objective: to liquefy the gas on site as soon as it's extracted, to store it on board, and then to serve as an offshore delivery point for LNG tankers. Of course, such a facility represents a monstrous cost, between $5 and $6 billion according to the experts. But, unlike investments in gas pipelines, the platform itself is reusable. In fact, once the field has dried up, the floating plant simply needs to be dragged ashore for maintenance, so that it can be put out to sea again to exploit another gas field for 20 to 25 years. With an estimated production capacity of 5.3 million tons per year, Prelude alone can supply enough liquefied natural gas to satisfy the needs of a city as populous as Hong Kong, with over 7 million inhabitants. The challenge for Prelude was to fit an entire liquefaction plant into a 488-meter-long building, the size limit imposed by one of the world's largest shipyards, and also one of the only ones able to accommodate a building of this size, Samsung Heavy Industries, located on Gohae Island in South Korea. In fact, the dry dock where Prelude was built can accommodate up to 4 container ships. This mega platform of unprecedented scale was built over 5 years, between 2012 and 2017. At the site's peak, 6,000 workers were mobilized. A true world first, the construction of a large vessel such as Prelude implies meeting some real technical challenges. Firstly, to compact an entire plant comprising hundreds of kilometers of piping, numerous boilers and storage tanks into a building less than 500 meters long. This meant reducing the plant's dimensions by a factor of 4, compared with a land-based installation. In the end, almost 600 engineers worked on the project to meet the challenge. Another challenge in the marine environment was anchoring this floating city. In fact, Prelude had to be moored to the seabed, so that it could remain permanently vertical to the extraction wells. Given the duration of its mission, between 20 and 25 years, it must also be capable of withstanding the most extreme weather conditions. What's more, unlike some floating oil rigs which can disconnect from the well in an emergency, Shell decided that Prelude should remain connected and operational in all weathers, in order to maximize its profitability. As a result, the anchor was designed and sized to withstand Category 5 cyclones, the strongest intensity on the Saffir-Simpson scale, equivalent to wind speeds of between 300 and 400 kilometers per hour. This technical feat was made possible by a set of 16 250-meter-long chains linked to giant anchors, 5 meters in diameter, sunk into the ocean floor. This operation is performed by huge hydraulic hammers, designed to work underwater. On the surface, the anchor chains are connected to the turret, an enormous vertical column that runs through the building and remains in a fixed position relative to the seabed and the well. Prelude can therefore rotate permanently around this axis to offer the least possible resistance to current, wind, and swell. A huge turret also houses 4 flow lines, long flexible umbilical cords, allowing gas to flow up from the well to Prelude. At 93 meters in height and 30 meters in diameter, it's the biggest fixed turret in the world. So gigantic that it could house the entire Statue of Liberty with its pedestal. Finally, the ultimate challenge for this giant of the seas is loading liquefied natural gas into LNG carriers. Normally, LNG carriers load and unload their cargo in protected ports. Here, they have to be able to tie up to a much taller vessel, on the high seas to boot, and operate in all weather conditions. Gas cooled to minus 162 degrees Celsius has to be transferred from a moving vessel to a moving ship over a period of 12 to 20 hours, the time required to carry out the operation. A real challenge, which required equipping the floating facility with 3 6,700 horsepower thrusters. To give you an idea, each of these thrusters has the power of the world's most powerful diesel locomotive built by General Motors. With such power, they can turn Prelude around its turret so that one of its sides is turned against the wind, so that LNG tankers can moor on the other, sheltered from the giant. The operation also requires 3 tugs to help the tankers tie up, and to intervene in the event of an emergency, as this loading operation in the open sea is particularly risky. In the event of a leak during the operation, the methane, which would revert to the gaseous phase, could ignite and cause the loss of the ships, and if it were to escape underwater, the risk would be no less great. The methane would then drastically reduce the density of the water beneath the vessel, and risk dragging its 600,000 tons, the LNG carrier and the tugs, to the bottom of the ocean. The crews are rotated to the ground by helicopter, thanks to a helipad adjacent to the living quarters. A real building, the same size as the Arc de Triomphe, which can accommodate over 300 people. The Prelude crew is supplied with food by boat, but remains completely self-sufficient in energy. The opposite would indeed be rather surprising, for a vessel whose gas reserves seem almost inexhaustible. With its revolutionary concept, the Prelude station will undoubtedly launch a new era in the naval and energy industries, as it enables us to meet the ever-increasing demand for natural gas while reducing production and transport costs for the energy industry, a solution with a bright future ahead of it. That's all for today. Thanks again to Surfshark for sponsoring this video. As a reminder, you get an exclusive offer and an extra 4 months free by clicking on my link in the description just below. Thank you all for watching this new episode, and see you soon on Looking For.